So are all able to see my screen, guys? It says special relativity.
Yeah, yes.
Fine. Okay, just a minute. I think I started the live stream. Okay. So it will be interactive session, guys. It will not be like one-way lecture. It will be interactive. Even I am very new to relativity, and it's a learning process for both of us. So now, can anyone say what do you mean by relative motion? Like, what do you mean by relative or relativity? Anybody?
When we express the motion of two, like let us consider an object A and an object B, and these both objects can be in a like inertial or a non-inertial frame. But when we try to measure the speed of, let us say, the object B relative to the object A, regardless of the speed, or yeah, like regardless of the velocity of the object A, that we term as special relativity. Oh, the normal relative motion.
Okay. So we got a huge number of terms which you said. So I'll just go by each term. Okay. So you told me something called as frame, or you told inertial and non-inertial frame. So what is a frame or a frame of reference specifically? It's nothing but a coordinate system. So for example, if you see my screen and there is a point here, how can I tell this location of this point? I need something to measure where is this particular point, right? So I can use something called as coordinate system to measure its location. So if you say my monitor is like 19 inch by 22 inch, I can tell this dot is approximately like some 10 inch and 5 inch height. So I can tell this dot to be 10 inch in from the left position and 5 inch above. So I can tell the location of this dot using a coordinate system. So if I say this is the coordinate system and this is the point, then we can specify its coordinate system, its location, using something called as coordinate system, which I mentioned it or represented by a letter S. So this is a simple Cartesian coordinate system where we have x-axis and here we have y-axis, and this location is say x comma y.
So to start with,
Okay. Now this is something called as a frame. Now this frame, we can also term it to be an observer. So say I am present and this is my coordinate system. Then I can tell this coordinate system to be an observer also. So who is an observer? Observer is a person who will measure something. He can measure the location of this point. He can measure at what time the point is present. He can find the distance between 2 points. So that is an observer, and we can also, the observer measures all this using something called as a coordinate system. So this is basically a coordinate system. If this coordinate system is moving, consider there are two people. One person is stationary and other person is moving in a car. So for person who is stationary, we will term him to be a person or a observer who is a stationary observer. So who is a stationary observer? Who is in rest. And who is a moving observer, or I can call him, moving observer. So moving observer is a coordinate system or a frame of reference who is moving with respect to the stationary observer. So he is moving with respect to stationary observer. So I will term the stationary observer to be S and this moving observer to be S dash. So there is one principle called as principle of equivalence. Yeah, just a minute, guys. Just a minute, sir. Um, is my screen still visible? Hello?
Yes, yes.
Okay. So consider two observers, say a person who is standing and there's a person who is in a car. So there's a car and there's a person here and he's moving like this. So with respect to this S observer here and S dash observer here, for S observer, S dash is moving. But for S dash observer, provided his velocity is V and its constant velocity, if the velocity of this moving observer, S dash observer, if the velocity is a constant, then according to principle of equivalence, he won't feel any force acting on him. He feels he is in rest and S is the person who is moving. So S will say, I am at rest, S dash is moving. But S dash will say the same, I am at rest, because he is in a constant velocity. That means he is in uniform motion, he is not accelerating. So he can say, I am at rest and S is moving. And both are correct. Nobody is wrong or nobody is right here. This is principle of equivalence. So this is obvious, this is true, right? For example, if you are in, if you're sitting right now in your room, and if there is a person who is moving in a constant speed in the car, both will feel they are at rest. But a person who is in car, he might see the surrounding environment and tell something is moving related to him, so he might be moving, he will think. But what if he is in a closed environment? He can't see anything outside the car. Then a slash person, he can't tell he's moving or he is at rest, because when he is in uniform motion, he cannot feel any external force acting on him. How can we prove this? So there is something called as Galilean relativity, which acts in low speeds. So it's very simple to prove, or it's fairly easy to understand also. Let me just yeah, I'll draw this. I'll draw a coordinate system. One minute. Okay. Say we have two coordinate systems where one is the S dash guy, the one more is S guy. So S is rest, S dash is in motion. So this frame of reference has a velocity V in positive x-axis. So this is x-axis, say this is y-axis. So the motion is only along x-axis. There is no motion along y or z axis. Then say there is a point here, some point P. So according to S frame, the person who is in rest, for him the location is t comma x. It's happening in some time t and at some location x. So here y and z are not changing, so I won't bother to mention them, but time and position is considered, right? So I'll just mention this point P according to S frame is at a location X and at some time T. But the same point according to S dash. So the one which I mentioned is according to S frame. According to S dash, it is sometime T dash and some location X dash is according to S dash frame. Now, how do we relate these two frames, or how do we relate these two coordinates? So it is simple geometry what Galileo used. So we know this distance is x, right? According to the geometry, this distance is x. Okay, x dash. Sorry, yeah. And the same point according to S dash or S frame. Sorry, S dash is x dash and S it is x. These dashes are confusing me. Sorry for that. But yeah, you understood this too, right? The location of point P with respect to S is x, and with respect to S dash is x dash. Now, what is the location of this frame? Say this origin is O dash and this origin is O. What is the distance between O and O dash? Anyone? So say this is, yeah,
X minus X dash.
okay, yeah, this distance is x minus x dash. So how do we relate this with velocity or time, or how we need an equation for this?
Yeah, we can say it's equal to Vx into t, right?
Okay, how is that possible?
Because distance equals velocity into time.
Okay, so say at time t equals 0, like t equals t dash equals 0, like at the beginning of the experiment, both the origins coincided. But as time proceeded, S dash is moving at a velocity Vx. So because of this, we can tell this distance to be Vxt. Why? Because at the beginning of time t equals t dash equals 0, both the origins coincided. Okay, so thus what do we get? We get an expression for x dash, right? Or I can tell x equals x dash plus vxt, or I can write x dash equals x minus vxt. So we got a relation between x coordinate and the x prime coordinate, right? Now, what is time relation? So according to Galileo, he assumed time to be universal. Time will be the same for any observer, he assumed. Thus, t dash equals t. And since there is no motion in y or z axis, we can write y dash equals y and z dash equals z. So this set of equations or transformations are called as Galilean transformation. There could be some spelling mistakes, sorry for that, but the word is important. So this is called as the Galilean transformations. So say this particle P is moving, then the particle has some velocity, right? So this particle here, this one is moving. Then it is moving, then it is having some velocity. S will measure the velocity to be u. S dash will measure the velocity to be u dash. So the particle P has velocity u according to whom? S frame. U dash according to S dash frame. How do we relate these two, u and u dash? It's fairly simple. Just differentiate this equation. I'll name it to be equation 1. Differentiate equation 1 with respect to t. Now see, t and t dash are equal. So dt equals dt dash. So dx dash by dt dash. This is the velocity of the particle according to S dash frame, that is u dash, equals dx by dt minus vx dt by dt. Now vx is a constant, right? So vx will come out of the differential operator. So what do we get? We get u dash equals u minus vx. Now if we differentiate this again, then we will get the acceleration of the particle, right? I'll differentiate this again with respect to time. So any idea, anyone, what will we get if we differentiate this again with respect to time?
Dash equals
Your voice was breaking.
A dash equals A. Is that what you said?
Yeah, you're right. So it will be du dash by dt equals du by dt minus dvx by dt. Now dvx is a constant, so this is constant, right? So it will be 0. So we get a dash equals a. Now if we just multiply the both side of the equation with mass m of the particle, we get ma dash equals ma, or f dash equals f equals ma, right? So the particle doesn't, or both the observers will feel the particle to have the same force m into its acceleration. I mean, both the forces are equal in both the coordinate system. So because of this, we can tell laws of physics are same in inertial frames. So inertial frames are those frames where the acceleration of the frame is 0, or the frame moves with a constant velocity v. Now, what if the frame is moving at a very high speed? And there is also a problem with this Galilean relativity when we try to measure the speed of light in different scenarios. For example, we know that speed of light is c, where it is given by 1 by square root of mu naught epsilon naught, right? According to Maxwell's equations, we get this. It is related to the permittivity and the permeability of the space. So its value is a constant, right? It comes around 3 into 10 power 8 meters per second. It's a constant value. It doesn't change, because even you move or don't move, the space is the same, right? In vacuum, if you move, it doesn't mean that the space property will change just because you move. But according to Galilean relativity, speed of light was changing. For example, consider a person here is showing a torch like this. So light is moving like this, right? So light is moving like this. This person is at rest, say S frame. But say another person who is moving with velocity v, and this light will go like this, right? The light moves. So what will the velocity of light be with according to S dash frame? So for S frame, the velocity of light is c. For S dash frame, according to Galilean relativity, we get c dash equals c minus vx. Say c dash equals c minus vx, where c dash is the speed of light according to S dash. So according to S dash frame, the person who is moving, he will see the speed of light to be different according to Galilean relativity or Galilean transformation, we say. But that is not true. Why? Because according to Maxwell's theory, speed of light is property of space. It is not dependent on observer. So to solve this problem, Einstein put forth this postulate. It's a very important postulate, that is speed of light. Speed of light is a constant, or I can tell it's a universal constant. And will be the same for any frames. Let the frame of reference be at rest, or let the frame of reference accelerate, or let the frame of reference be in uniform motion. For any observer, whatever be his motion, speed of light is the same for him in vacuum. Speed of light in vacuum. So this is one of the fundamental postulates that Einstein used, and this is fairly true in every scenario. Speed of light doesn't change. So if speed of light doesn't change, what the transformation should be so that the speed of light is a constant in every frame? We need a set of transformation, a new type of transformation to follow this postulate. And then we, when we build the idea logically, what do we get? We know that say the person or the object or the location is measured with respect to x-axis only. To keep it simple, we know c equals x by t, right? Where x is the position of light, so we know the speed of light is x by t, where x is the position of light. Or I can write x equals ct, right? So this is according to S frame. According to S dash frame, c has to be constant. C doesn't change. That's our idea. So it is c equals x dash by t dash. Then we get x dash equals c t dash. Now we want c to be equal in both the frames, right? So what will I do is I'll square both the sides. So c square t square minus x square equals 0. Here it will become c square t dash square minus x dash square equals 0. Since speed of light is same in both the frames, I can equate them. What do I get? I get c square t square minus x square equals c square t dash square minus x dash square. So this is one of the important equation that will help us in getting the Lorentz or the transformation rules that will keep speed of light to be a constant. And we get a relation between x dash and x, t dash and t to be, anyone, any idea? If anyone remembers. Okay, I'll write it. It is x dash equals x minus vt by square root of 1 minus v square by c square. I can write this factor 1 by square root of 1 minus v square by c square to be some factor gamma. It has a name, I'll come to that. Then we get this x dash to be gamma into x minus vt, and t dash will be t minus vx by c square whole divided by square root of 1 minus v square by c square. So it will become gamma into t minus vx by c square. So this transformation is known as Lorentz transformation. It's a very important transformation and a formula that we need to remember. So just remember gamma. What is gamma? 1 by square root of 1 minus v square by c square, where v is the velocity of the frame. It's a constant value. C is the speed of light. It's a constant. So gamma is a constant for an observation. And the primed coordinates x and t dash, x dash and t dash, and the unprimed coordinates x and t are related by this equation called as Lorentz transformation. So any doubt in this? You can unmute and ask. I'm not able to see the chat box. You can unmute if there is any doubt. And we can also write y dash equals y and z dash equals z. Why? Because there is no motion in y and z axis. So have you understood this, guys?
So this is one directional motion, right? So if we consider a 3D motion or even a 2D motion, would we be dealing with the components of the vectors, rectangular components?
Yeah. So in that time, what we will do is say, it's a very good question. Say we have a 3D S frame and a 3D S dash frame, and it has velocity in some direction. Say Vx I cap plus Vy j cap plus Vz k cap. So this is y axis or y dash, z dash, this is x dash, and these are the unprimed coordinates. Now it's a very complicated scenario. Why? Because Lorentz transformation in 3D is a very big transformation where we need to remember so many so many formulas we need to remember. But we can make it simple. Does anyone have any idea how we can make this scenario simple? Any idea? Yes.
We can redefine the frame.
Okay. So redefine in how? How should we redefine this? So
We can
keep the x-axis. We can keep the x-axis such that it is along the velocity.
exactly.
And then we'll have the same Lorentz transformation.
So what should we do is make a rotation so that this velocity vector is brought to x-axis of the rotated coordinate and then apply Lorentz transformation. So we know what is rotation. Like I don't remember the set of equations, but we can define x I to be some rotation matrix times xj. So I can do some rotation so that this velocity vector will be such that it should be in the x direction of the rotated transform or the rotated coordinate. Then I can apply Lorentz transformation and make it a transformation only in x in the rotated transformation in the rotated coordinate. So that's how we can simplify this three-dimensional coordinate transformation to just one-dimensional Lorentz transformed coordinates by using a rotation and then Lorentz transformation.
But for that, like we should also know how the velocity will transform when we rotate the coordinate, right? Like the velocity shouldn't transform when we rotate, like not shouldn't transform, but we should know that.
See,
Like we are taking one more frame altogether, right?
but the velocity is the same, right? See, just because you rotated the transform, rotated the frame, it doesn't mean that the frame will change its direction. No. For example,
Yeah, that's
say,
how. Yeah,
say you're in
continue.
a car moving in some arbitrary direction. You're in a car moving in some arbitrary direction. Okay. So if you just see in different directions, you're not moving in different direction. But if you're just seeing in different direction, it doesn't mean that the direction of car changes, right? Got it?
Yeah, actually, that's what our intuition tells us. But since this, like, the transformation from a rest frame of reference to a moving frame of reference turned out to be this complicated, like Lorentz transform. So how are we sure a rotation wouldn't change it, like, somehow weirdly? How do we know that?
So take this as homework. Find out the rotation matrix, apply rotation, and then find out the Lorentz transformation. And then apply 3D Lorentz transformation. I think you can get both the relations in Google. Do both, and you will get that both will be the same. Applying rotation and then Lorentz transformation will be the same as applying 3D Lorentz transformation. You can verify that.
Okay, fine. Thank you.
Okay. So,
Sagar,
Yeah.
so you wanted to rotate the coordinate system such that x axis coincides with the direction of velocity, right? So
yes.
even then, y-axis and z-axis will both experience a variation, right?
Okay, wait. I'll just do it 2D and show you guys. So, say we have here x-axis, here y-axis in S, and we have x dash and y dash in S dash. So, say the frame is moving like this. It has vy component and vx component, this velocity vector. So v vector equals vxi cap is vg vy cap. Now, if we apply the transformation of this coordinates such that the transformed S is like this and the transformed S dash is like this and the velocity is like this. Now I'll just write the transformed x to be u. I don't need to use u. I need a new variable. Okay, I'll write it capital X. This is capital X, this is capital Y, and this is capital X dash. This is capital Y dash. Now what you can write? You can write X dash equals gamma X minus. So V is the same. The magnitude of V is same. It doesn't change, right? So it will be Vt and T dash. So T dash will be the same T and Y dash will be Y. So both are same. Got it? Any doubt in this? So
Okay, I
how
got
do we relate X and X dash? I mean not X and X dash. How do we relate X and X? X dash and small x dash. This is got by rotation. So I remember rotation matrix to be sin theta cos theta minus cos theta, or maybe sin and cos are interchange. I don't remember exactly, but it will be somewhat like this. It's the rotation matrix. You can use this matrix and get the relation between these two. So that's just an algebraic problem. But our 2D Lorentz transformation is just now 1D Lorentz transformation in the rotated system, right? So it's the same way you can do it for 3D also. Is it not clear? Hello. Okay. Now we will come to something called as the four vectors. So it is fairly an important concept. Four vectors. Now, special relativity will deal with four variables. That is, three variables of space x, y, and z, and one variable of time. So all these are interlinked according to Lorentz transformation, right? So space and time are interlinked. The transformation of space has a time variable. The transformation of time has an x variable. So it physically it tells us that space and time are interlinked. So space and time can be treated equally. So if you're moving in space or if you're moving in time, it is somewhat related. So through length contraction, you will get to know that farther you moving. Okay, I'm sorry. In time dilation, you will get to know that faster you move in space, slower you move in time. So something like that, right? We get that idea. So what do we get is space and time are interlinked deeply. So this four vectors is a quantity or a physical quantity that has four components. Usually we know in our 3D space, say for a vector in 3D, this is z-axis, y-axis, and x-axis. So if that is a vector v vector, some vector v, it has different components. It can be written as vx I cap, vy j cap, plus vz k cap, right? You can write this. So how are the components written? I can write v vector to be vx comma vy comma vz, right? In just component notation, I can write this. In x component, its velocity is vx. In z component, its velocity is vz. So this is the component form of writing a vector. But in four vectors, we have an additional component of time. So say some vector v, it has 4 components. I'll write it to be vt. It is the time component, vx, the x component, the y component, and the z component. So it has 4 components, and hence the name 4 vector. So the time component is similar to, for example, if we say the location or the position of something, say x, the position, or I can write it to be, I'm getting noise. So if we say position, say I'll say to be like p, the coordinate, the particle is in this position. I have 4 things to be needed, right? They are time, x position, y position, and z position. But if we are dealing with 4 vectors, we need all the components to have the same dimensions. So that is one necessity for 4 vectors. So what I'll do is, to have the same dimension of the time component, I will multiply t with c. So this has the dimension of length, and all this, as you know, has the dimension of length. Only for dimensional equality, I have to multiply time with speed of light to make it dimensionally equivalent. So this is a 3D or a 4D position. I will name it to be S. Now, how about displacement in 4D? So we know in 3D, dr vector is dx I cap dy j cap plus dz k cap, right? This is the displacement vector in 3D. Similarly, in 4D, it is c is a constant, so c dt, dx, dy, dz. This is, I need to introduce some concept to write the left hand side. I'll introduce that concept and then come back to this. So how is this denoted? So I'll quickly introduce a concept called covariant and contravariant. Covariant and contravariant vector. So now covariant and contravariant vector are two types of 4 vectors. So there are 2 types of 4 vectors called as covariant and contravariant. What does this contravariant 4 vector mean? Now, how do we denote this contravariant 4 vector is, we denote the components. See, we know any 4 vector has 4 components, right? It has time component and 3 space components. So we can denote time component with an index 0. For example, if I write v subscript 0 or superscript 0, it refers to time component of vector v, or component of 4 vector v. If I denote it by v1, remember it is not power, it is an index written as superscript. V super 0 is V superscript 0. It is not power, remember, it is just an index of this number. So V1 is x component. It's the same. It's x component of V vector. V super 2 is y component of V vector. V super 3 is z component. So this is how we will show the components of some vector V. I can generalize this with V super mu, where mu equals 0 or 1, 2 or 3. So V super mu is V0, V1, V2, V3. V0 is the time component. V1 is the x component. V2 is the y component. V3 is the z component. So this is a vector, a 4 vector called as contravariant. So mathematically or notationally, the index is a superscript for contravariant. But if we write the covariant vector, it is same, but the index is written below. So it will be V sub 0, V sub 1, V sub 2, V sub 3. So this is the time component. These are space components. So for contravariant, the index is superscript. For covariant, the index is subscript. So this is a covariant 4 vector. Okay. Now, how do we relate these two vectors? We need a relation between covariant and contravariant vector. So what I'll do is I will use the matrix notation to understand this. I can write the just a minute. Okay. I can write this V sub mu in a row matrix. Covariant vectors are written as row matrix. Contravariant vectors are written as column matrix. This is a convention. So I can write this covariant vector. Just a minute. So we need a relation. So we will use matrix notation. Covariant is written as row matrix. Contravariant is written as column matrix. And the relation is just a minute. Okay. So the contravariant is related like this. We have the column matrix first. This is contravariant 4 vector V super 0, V super 1, V super 2, V super 3. That is equal to something called as a tensor or some 4 by 4 matrix and multiplied with we need this to be following the rules of matrix multiplication. This 4 into 1 and this is 1 into 4. I think I messed up. So first it has to be the row matrix. Yeah. So we need first the row matrix. It's 4 into 4, this is 4 into 1. And here we have the row matrix B sub 0, B sub 1, B sub 2, B sub 3. Now, what are the entries of this 4 by 4 matrix? The row matrix is covariant. The column matrix is contravariant. This 4 by 4 matrix is called as the metric tensor. This metric tensor is a diagonal matrix where the diagonal elements are 1, minus 1, minus 1, and minus 1. So the rest of the elements are zeros. Now, this covariant matrix, I can denote it by V sub mu. The contravariant vector, I can denote it by V super mu. This metric tensor, I can denote it by G in the subscript only. We have mu, and I'll write it to be new, and this to be new. So mu and nu are just indices. So the Greek letters mu and the Greek letters mu and nu, they are just indices. They run 1, 0, 1, 2, and 3. These are the values. So I can write this relation in this form, where V sub mu is the covariant vector, V super nu is the contravariant vector. Mu and nu are just indices. Their values are 0, 1, 2, and 3. And this metric tensor is it's the sign are also convention. The sign what I am using is plus, minus, minus, minus. Some authors use minus, plus, plus, plus. So it is just a convention. This is the convention what I will use, and I think even Dishan sir will also use the same convention. So this is how we can write the relation. If you notice, the subscript index is mu here, right? When the subscript index is mu, here we have subscript index mu and nu, but we also have a superscript index nu, right? Subscript and superscript are somewhat cancelling each other, but I mean, sorry, the superscript and the subscript news are somewhat cancelling each other, but is subscript mu is there, no, that is remaining. So it is somewhat balanced. See this equation V super mu G mu mu V mu. This is not balanced. Why? Because here we have a superscript mu and here we have subscript mu, but they're not cancelling each other. But here we see it is both are in the subscript only. They're not like one is in superscript, one is in subscript. Got it? So actually, what I'll do is I will end the session now, because if you want to go deep into this, We can take like 2-3 hours more, but it's pretty late now. So I will end the session now, and I think we can continue this concept still furthermore in the next week. So I'll just clear doubts now. So if there is any doubts, guys. Yeah, Pragna, this note should be shared. I'll share this notes. So if anyone have notes, if anyone have doubts, please raise your hands. Sashwat, you raised your hand.
So,
I think,
Sagar, are there any
yeah.
physical significances of covariant and contravariant?
Yeah, there are physical significance and intuitions in this, but I need another session to go deeply into them, because now even if I do quickly, it won't be right. Like I won't do justice to the concept. So there are very good intuitions, and they all are related due by the definition of how we transform the coordinates. Covariant vectors are transformed in one sense, contravariant vectors are transformed in the different sense. So how they change or how they are transformed, that defines what type of vector it is. So there is more for this. We'll cover that in next week.
Thank you, Sagar.
Okay, and I will give you some reference that will be very helpful. So the first one is there's a YouTube playlist by Faculty of Khan. So he will there is a playlist on tensors. So please go through this. There are like 9 videos. Each videos are approximately 10 minutes only. In like 2 hours, you can get a grasp or understand the notations at least. So this Faculty of Khan is a YouTube channel, and he has a playlist called Tensors. This is one very important playlist. And the second one is a book by Sean Carroll. Sorry for the spelling, there might be mistakes. His book on general relativity. There is first few chapters on special relativity in this book. They're very good, and one thing to remember is the signature what the metric signature what Sean Carroll uses is minus plus plus plus. That is in his diagonal matrix or the metric tensor by Sean Carroll. He interchanges the symbol of this entries. If you just take care of that, it will be pretty simple explanation, and the math or the physical intuition is the same. And the third one is you can also visit Griffiths. So Griffiths electrodynamics book has a chapter on relativity. So that is also very good one. And I learned most of the special relativity topics from playlist by Leonard Susskind. So he's a very great scientist in the current times. Leonard Susskind's special relativity. Playlist or lecture series. So this Leonard Susskind book, along with Sean Carroll's, these two I followed them and then got a good knowledge of relativity. So go through them, and I recommend going to tensors. This is very important for the next class. So for this tensors playlist, please go through that. The initial videos are very easy to understand, but the ending videos might be little tough. I will also do that, explain it neatly, and then I will continue. So that's it, guys. So yeah, If there is any doubt, you can discuss in Discord channel. There is 2 channels for cohort 1 and cohort 2. You can discuss there.